Hello and welcome to our first revision lesson on waves. Now I'm going to talk through a large chunk of waves in this PowerPoint. It won't be all of it because, as you can imagine, that is a hell of a lot of information, but I will try my best to get through as much as possible, and then I'll just keep on making videos and each lesson give a little bit more. And yeah, we'll just keep on doing questions. It does mean some of the questions that you do in each lesson might be on stuff we haven't quite covered, or recovered I should say, because I'll just give you general wave questions. But I'm hoping this video will remind you of enough that you'll be able to do the questions. That's a plan anyway. So here we go, waves, waves, waves. So first bit is you need to know a definition. Waves transfer, in fact, hang on. Let me change this. Oh no. I feel like such an old person. How do I get this? Okay, I'm just going to delete it. Progressive waves, that's what I was looking for. Transfer energy from one place to another with no transfer of mass. And you need to know that definition because it's very handy. So, general bits about waves. On a transverse wave, the top is called a peak or a crest, the bottom is called a trough, and I always tell my year 10s when they do it that it's like a little piggy trough. I even make the noise. The amplitude, I mean, again, younger years, I say the height of the wave. Let's say the distance from the equilibrium position to the peak of a wave. Or, it's a bit big, isn't it? Should not be editing this whilst doing the video. Hey ho. The distance from the equilibrium position to the peak of a wave, or to the trough of the wave. You can go down as well. Wavelength shown by the Greek letter lambda, the length of one complete wave. So distance peak to peak, or trough to trough, or equilibrium position to the same equilibrium position. Frequency, the number of oscillations in 1 second, measured in hertz. 50 hertz is 50 vibrations or waves or oscillations in 1 second. The reason it is very handy for you to know that is they quite often don't say the frequency is 50 hertz. They might say 100 waves pass a point in 2 seconds. And you have to think, okay, that means it's 50 waves in 1 second. Okay, the frequency is 50 hertz. An equation that people seem to forget all the time, because it's just not complicated enough for them to remember it. Frequency is 1 divided by time period, and time period is 1 divided by frequency. Very handy. Okay, so definitions of transverse waves. The vibrations are at right angles to the direction of energy transfer. Lovely jubbly. Examples: any electromagnetic spectrum wave is a transverse wave. Water ripples as well. In longitudinal, the vibrations are parallel to the direction of energy transfer. Don't forget you also have compressions and rarefactions in there. Lovely. Examples: any sound or sonic wave, ultrasound for example. And now, your bog standard equation. This is a wave equation with a bit of A level thrown in. So the time taken for one complete oscillation is at period t. In this time, the wave will have moved one wavelength, lambda. The speed of the wave, therefore, is distance divided by time, lambda divided by t. Remember that 1 over t is frequency, so v is f times lambda. One wave equation with a bit of derivation there. Boom diggity. Right, I'm actually going to miss out the phase difference bit because I know it's officially in the first chapter on waves. However, it kind of makes sense for it to be, when I recap it, in with the superposition and interference bit. So I'm going to leave it for the time being and do it in another video. So let's go on to law of reflection. Again, you've seen this many a time. Instant rays is your ray of light coming in. It will always bounce off a surface at the same angle that it comes in at. So angle of incidence equals angle of reflection. Remember that normal is the dashed line that you draw at 90 degrees to the surface. Okay, refraction. The speed of light depends on the material through which the light is travelling. When light enters a different material, e.g. from air into glass, the speed of light changes. This causes the light to bend or refract. The speed of light is affected by the density of the material through which it is travelling. Lovely. Here you've got light going from a low density into a higher density glass and then out the other side back into air, a low density. When it is going into a material with a higher density, and later on we'll talk about a higher refractive index, the light bends towards the normal. When it's coming out of a material with a high density and a high refractive index, it bends away from the normal. So refractive index n tells us how light travels through a substance in comparison to a vacuum. It is a ratio, so it has no units, and you can work it out with this equation. N is c divided by v. So n there being refractive index, no units, it's c, the speed of light in a vacuum, 3 times 10 to the 8, divided by the speed of light in the material, v. So you should always end up with a refractive index that is over 1. You should never have something that's 0. You're looking at 1.2, 1.6, etc. Can't say I've ever seen one that's 2, but I wouldn't rule it out. So the larger the differences between the refractive indexes of substances, the more the light will change direction as it enters the substance. Oh, there you go. So on the left-hand side, you've got light going from a material with a refractive index of 1 to 1.3. Small bend. There we go. On the right, you've got it going from 1 to 2. So clearly refractive indexes of 2 do exist. And you can see it's a much larger refraction there. So there is a refraction law here, which has been called in the past Snell's law, hence why we've got Willebrord-Snellius at the top. But actually, they've rechristened it as the refraction law because Ibn Sahl discovered it over 700 years earlier than Willebrord-Snellius. But, you know, whitewashing of physics, there we go. So, n1 sine theta 1 equals n2 sine theta 2. n1 at... gosh, this formatting has gotten a bit funny, isn't it? There you go. Right, n1 is the refractive index of the incident material. Sine theta 1 being the angle of incidence, and 2 the refractive index of the second material, and theta 2 the angle of refraction. If you are not given all of the refractive indexes, you're just told it's going through air, the refractive index of air or a vacuum can be thought of as 1 to make your life easier. So just add that into your equation. So, total internal reflection. The incident substance has to have a larger refractive index than the other substance. So this is like if the light is travelling from glass into air. The incident substance is glass, it's got a higher refractive index than air. And the angle of incidence exceeds the critical angle. So we're looking at total internal reflection, which I realise I didn't actually say. This is where you basically, although the material is not a mirror, it will have all of the light bouncing off of it internally. So the way this happens, as I say, is you've got to be going from a thick material into a thinner material, and you've got to have a large enough angle to exceed what is called the critical angle. So here we've got 4 different scenarios looking at the diagrams. On the left-hand side, you have light going from air into glass, and you can see because it's going into a thicker material, the light bends towards normal and it slows down. The second box in, glass into air, the light is bending away from the normal because you've obviously going into a thinner material. Now, all of the 3 on the right hand side are actually light going from glass into air. However, you can see that they've increased the angle that the light is going in at. Remember, the angle of incidence is always measured between the ray and the normal. So as it gets bigger and bigger, this third one, which is entitled critical angle, is the exact angle which causes the light to all go along the surface of that glass. So it's refracted at 90 degrees. That's what a critical angle is. As soon as the angle is bigger than the critical angle, which is what you're seeing on the right-hand side, that's when we get total internal reflection. An equation that links this, n of the medium, so the refractive index of whatever material you're looking at, is 1 over sine of the critical angle. Okay, diffraction. Basic thing, waves spread out as they pass through gaps. So you're looking down on some wave fronts here. And then you can see as they're coming to a gap and there's 2 walls there, that you're getting that nice circular pattern. Diffraction works best if the gap is about the same size as the wavelength, and that's very key. They love asking you about that, so keep that fact in mind. If the gap is too large, most of the waves pass straight through and only curve at the edges, and that's what you're seeing in this picture. Okay, we're nearly at the end here. Polarization. Transverse waves can vibrate in many different directions, all at right angles to the direction of travel. Longitudinal waves can't do this because all of their vibrations must go parallel to the direction of transfer. We know this. So polarization filter only lets vibrations through in one direction, and it only works on transverse waves. So if you have a look at the diagram, on the left-hand side, you've got a wave which is transverse, but you can see it's vibrating in lots of different directions. After it's gone through the polarizing filter, it will only vibrate in one direction. So it's a really good way of proving that things are transverse using polarization. Plain polarized light, once it's been transverse, will have half the intensity or brightness of the original light. And that's quite handy to remember. So intensity, the word I've just used. Intensity is power divided by area. The official definition are radiant power passing through a surface per unit area. The units are watts per square metre. So intensity is power divided by area. Again, people always forget that. Now that area that can be covered can be lots of different areas. So we're going to look at one now, which is the area of a sphere. Because intensity depends on surface area, and the surface area of a point source of light is a sphere, surface area of 4 pi r squared, intensity is inversely proportional to the square of the distance from the source. So we call it an inverse square law. You can see on the right-hand side there's an equation, I is p over 4 pi r squared, where r is the distance from the source. Right, that was quite intense. I hope you've got all of the information you need for the time being. There are some questions to crack on with, and I'll see you soon.